In this chapter, we will first look at the various operations available for implementing sequential processes. Then we move on to the operations which allow us to implement structured programming techniques.
We also see how modular top-down programming can be implemented through the use of subroutines.
In the process, we will also be studying the C specifications in detail.
First, let us look at the basic arithmetic operators supported by RPG 400.
We have add, subtract, multiply, divide. Let us look at the add operation. If we want to add two numbers num1 and num2 and store the result field in a field sum, we code num1 in factor 1, num2 in factor 2 and sum in result field. We also specify the length of the result field if it is a new field. Suppose we want to add num1 to sum, we code it like this. An entry is required in the result field and you can have an entry in factor 2 only or both factor 1 and factor 2. Also, factor 1 and factor 2 could contain literal values. Similarly, for the other operations. There are also some operations that are used to assign a value to a field.
For numeric fields, you have 0 and add and 0 and subtract.
For character fields, you have the move and move left operations. The 0 and add operation is used to reset the value of a field specified in the result column. This operation initializes the count field to 0 and then assigns the value of factor 2 to it. It is most useful for initializing fields to 0. The 0 and subtract operations work similar to the Z add operation. The value of the factor 2 field is multiplied by -1 and the product is stored in the result field. The move operation is used to assign a value to a character field. Factor 1 is not used in the move operation. Factor 2 can contain a field name or a character literal coded in apostrophes. The move operation transfers the characters from the field in factor 2 to the result field starting with the rightmost character. If the result field is smaller than the string in factor 2, the excess character to the left will be truncated. If the result field is larger than factor 2, then the access character in the result field will remain in the unused positions. This type of error can be overcome by coding a P in position 53. This causes blanks to be padded automatically in the unused positions. The move left operation is identical to move operation except that the characters are transferred starting with the leftmost character. Here also The pad option can be coded in position 53. RPG also provides a set of built-in literals called figurative constants that we can use in the operations we just saw. The figurative constants are star blank, star 0, star HIVAL, star LOVAL, star off, star on and star all. They have a predefined value and take on the length of the field they are associated with. If we may move star blank to a character field, the field will be filled with blanks. Star HIVAL and star LOVAL can be used with both character and numeric fields. Moving star HIVAL to a field causes it to be filled with the maximum possible value the field can hold. Star 0 is also used with both character and numeric fields. It causes the field to be filled with zeros. Star all is used along with the character's string. The string is cyclically repeated to fill the total length of the result field. The constants star on and star off represent 0 and 1 respectively. It is used to set on or off the RPG indicators or to move either zeros or ones to a character field. Let us move on to the relational operators. We have 6 relational operators: greater than, less than, equal to, not equal to, less than or equal to, greater than or equal to. When two numeric items are to be compared, the system does a comparison based on algebraic values. When character values are being compared, the system uses the EBCDIC correlating sequences and compares character by character starting from the left. These relational operators are used along with the selection operations to specify flow of control within a program. Let us study the selection operations available with RPG 400, which allow us to modify the sequential flow of control within a program. We have the if then else statements, select, case, do while, do until, leave and ITER. Let us begin with the if statement. It is written like this. The value in factor 1 is compared with the value in factor 2 according to the relational operator. All the statements following the if statement and up to the end if statement are executed. If the condition is not satisfied, the statements are skipped. For example, here we say if a color is yellow, then add it to yellow count. Next, we move on to the if-else condition, where we can also specify what has to be done in case the condition is not met. For example, here we say if color is equal to yellow, add 2 to yellow, otherwise add 1 to other. You can also use the AND or OR operator to specify compound conditions. For example, we say if the amount is greater than or equal to 10,000 and type is equal to A, subtract discount A from amount and store it in total. Otherwise, the discount B should be deducted from amount and placed in total. When an AND is used, both the conditions have to be true. With an OR condition, only one of the conditions need to be satisfied.
You can also have nested if statements.
Here is a flowchart showing nested if statements and the corresponding RPG program. Complicated if statements can get very confusing. The select and case operations are a solution to this. This is an example of a select condition. The select operation is written first to indicate the beginning of a select construct. This is followed by one or more lines or where conditions to be tested. Each condition is checked sequential starting with the first. As soon as a condition is satisfied, the calculations that follow it are executed and control is passed to the end of the select construct identified by the end select or end operation.
If none of the conditions are met, no operation will be performed.
However, if we want to have some operations performed in case none of the operations are satisfied, we can specify this by using the other statement. In the select statement, we code the statements that have to be executed for each condition on the lines immediately following the condition. The case operation is almost similar to the select. When using case, we write a separate subroutine for each condition. In the case statement, we pass control to the corresponding subroutine. The conditions are checked sequentially one after the other starting with the first. In the first condition, if the value of the amount is less than 10,000, the subroutine sub RA is called. When a condition is satisfied, control passes to the corresponding subroutine. Control then passes to the end of the case statement identified by an end case or end operation.
The remaining conditions are not checked.
As with the select, here we can specify a subroutine to be executed in case none of the conditions are satisfied. For this, we write a case statement without any relational operators.
Next, we move on to the iteration constructs. Let us look at the do-while loop first. With the do-while operation, you can use any of the 6 relational operators. The field or literal in factor 1 is compared with that in factor 2 for the condition specified on the do-while operation.
If the condition is true, all the statements between the do-while operation and the end-to operations are executed. These statements will be executed continuously until the condition becomes false. With a do-while condition, the condition is first checked and the statement executed only if the test is successful. You can also have compound conditions for looping. Next, we have the do until operation. This is very similar to the do while operation. When the do until condition is used, the statements are executed first before checking the condition. This ensures that the statements in the loop are executed at least once. Sometimes you need to execute a loop a fixed number of times. For this, we have the do loop, which executes the statements coded with do and do statements as many times as specified in factor 2. Do automatically increments an internal counter each time through the loop. There are a number of options you can specify with the do loops. The initial value of the counter, an increment value which is to be added to the counter each time through the loop, a final value of the counter at which looping should stop, a field that can be used to capture the current counter value. You can omit one or more of these values, in which case default value of 1 will be assumed for them. Next, we see two operations that provide flexibility of exiting from a loop before reaching the end of the looping cycle. They are leave and ITER. When you want to skip some of the instructions in a loop and begin the next cycle, you can use the ITER operation. It causes the remaining statements in the loop to be skipped and control passes to the beginning of the loop to begin with the next iteration. The leave operations allow you to completely break out of the loop. Control passes to the next statements following the undo or end operation. RPG also allows us to use a top-down modular approach to programming through subroutines. A subroutine in RPG is identified by the begin subroutine and end subroutine operations. Factor 1 contains the name of the subroutine. To execute the subroutine, we have the execute subroutine operation. The execute subroutine operation causes control to pass to the subroutine named in factor 2. The statements in the subroutines get executed and on completion, control passes back to the statement following the EXSR operation. In RPG, a subroutine is not allowed to call itself, that is, recursion is not allowed. With that, we have completed the second chapter. Summary. In this chapter, we have looked at the various operations available for implementing sequential processing. Also, we looked at the operations to implement structured programming techniques.
We also saw how modular top-down programming could be implemented through the use of subroutines.
We have studied the C specifications in detail.